I'll start by introducing the first speaker. So Dr. Wilson Leal da Silva is a product manager at the Danish Institute of Technology. His fields of interest include cement and concrete technology, in particular mixed design and testing of ready mixed concrete, self-compacting concrete, high-performance concrete, and mass concrete. So his experience results from activities developed in a series of countries, in Brazil, Czech Republic, Denmark, Germany, and Switzerland. And at present, he works on topics such as 3D concrete printing, concrete inspection using drones and AI, artificial intelligence, as well as software solutions applied to concrete technology. Also, he works on the preparation of project proposals within the Horizon 2020 framework. So I'm extremely pleased to be able to introduce Wilson, and Wilson, over to you.
Thanks for the introduction. I can start by sharing my screen here. And okay, so I presume you all can see what I see here. Yes, good. Thanks, Boston, for the heads up. Yes. So yeah, thanks for the introduction. Once again, it's a pleasure first to be invited to present at the BAM event. I've known Chris for a couple of years already, and also Professor Knack back to 2015 when I started working here at the Danish Technological Institute. And yeah, unfortunately, not a physical meeting this time, but we get the best of what we can get out of online events. So let's give it a try. So today I'll be talking about 3D concrete printing, and the title in the program is actually 3D concrete printing, an overview, but I added an extra set of words there. It's an overview of current trends. There's a lot going on in the 3D concrete printing world, but I'm trying my best to focus on what is new over the past few years. And I've been working in the field of 3D concrete printing and additive manufacturing, cementitious material. It dates back to 2016. So I hope I can bring some new insights to the audience. So the topics I will be covering on my presentation. Just go on. Trying to pass this one. All right, there we go. I hope you will not start jumping around. All right. I'll focus mostly on aspects related to materials, concrete extrusion or extrusion as per se. So I'm talking, when I say 3D concrete printing here, I'm strictly focused on extrusion-based methods. There are other methods out there, but I'm going to focus on that topic. And then I jump into some details regarding reinforcement within additive manufacturing processes. And last but not least, I will talk something about the latest applications that surfaced the media over the past 2 months. So from materials, in a fairly simple way, the challenge with 3D concrete printing, yeah, from the very start, is that now we have this duality that we want a material that is flowable, so we have no problems to pump it to pump it through a stream and then reach the robot nozzle. But at the same time, we want that to be stiff at the extrusion point, so you can start stacking up layers. And this brings some challenges, because if your material is extremely fluid, you might run into the risk of flow out when you're extruding a material that is too fluid. So you basically make a slump test out of your printing. And if it's not stiff enough, you might still be able to extrude and stack layers, but suffer from an effect called buckling. So you have a slender element that will just buckle out and fail. So this competition of physical characteristics of the material are roughly translated into two properties. One of them would be yield stress of the material, so how much shear stress or how much stress you have to put into the material so it starts flowing. And the second would be elastic modulus, that would be more relevant to the buckling part of the layers you are printing. So if you look at the chart, if you are somewhere within the green zone, you prevent the two failures from happening, the flow out and the buckling. But okay, how this is known, and there has been a very interesting publications in the beginning of research of 3D concrete printing. But how are we here at DTI mapping these characteristics so that we can start using material properties to simulate the behavior instead of having only rough estimates. And that's the current trend number one, that we are jumping towards from rough estimates of the material behavior into actual material models that can describe what's going on during your 3D printing process for the benefit of being able to truly simulate what you're going to print. Because in most cases, you can be challenged on, depending on which kind of geometry you're printing, and then you might not always know whether your material will have enough use stress and elastic modules to cope with all the stresses related to the geometry. So first part relates to rheology. And then in these two charts I have here, I'm showing on the left side, it's a rotational test that measures basically viscosity of the material. So I have the initial yield stress as the point where the red curve is hitting the vertical axis, and then the slope of the curve will dictate the material viscosity. On the second part is an oscillatory test of a strain scan to identify at which level of strains, at which level of like material strains, when you're stacking and squeezing one layer against the other, the material behaves as a linear viscoelastic. So when it's actually, you can expect the material to behave as a linear material on that part, or linear elastic material. So the information from these two tests can be put into a elastoviscoplastic constitutive model, and don't make too much hassle about all these physical interpretations of this dashpot, spring, and the slippage model. The idea is that this is a little box that defines how your material behaves when you stack layers. So we run experiments in the laboratory where we do a few test prints, use the material characteristics that we measured using rheology, and then we validate CFD modules, so computational fluid dynamic models, that will be able to describe what is the shape of my extruded layer. So we validated and recently published this. I have a link to the source, and I'll share this presentation at the end of the event. We validated a CFD model that describes the shape of extruded layers. And the benefit here is that now, instead of us making 10 or 15 trial prints, I can reduce the number of trial prints I have in the lab by only making the material characterization and relying on simulation, on numerical simulation, to optimize the number of tests I have to do in order to identify a mix that's first printable. And then comes the second part now. The second part is, can I stack it? So let me go to the next slide. There you go. So the second part, the second part is, can I stack these materials? In that case, we are running a set of different measurements. So again, don't get too confused about the charts. The main information here is the chart on the left. I'm mapping what is the development of storage modules, in that sense, the elastic response of the material to loads over time. And then in the black chart, I'm measuring the creep behavior. So when I sustain a load into a layer, how much is the deformation post the immediate load? So you have like the compliance function, or how much the material creeps over time. And this allows us, again, to feed a different model. And in this case, it's a Maxwell material that it's an elastic, how to call it, elastic creep. It's elastic model with a creep response, which is dependent on both time and temperature. So the information from the chart on the left side, the white chart, gives me these D components, and the information from the creep compliance will give me the deformation over time. And then similarly to this fluid part, on the solid part, we do experimental tests where we are monitoring the deformation using like high resolution cameras to run digital image correlation tests. And these digital image correlation tests allows us to map what is the deformation of a layer during the printing process. So this information is then used to create a finite element model. And then we use the experimental information from the test with the finite element model to see, hey, is our model compliant? I mean, is it describing the phenomenon we observe in the laboratory? Yes or no? Once this is all validated, now we have both a model describing the fluid characteristics of the material and a model describing the elastic characteristics of material. When these are two combined, then we are in the sweet spot of 3D concrete printing that now we have, and all of this work I'm showing here is still in progress here at DTI with a number of partners from Denmark. But the idea is that once these two models are combined, and then I have a smooth transition between what's being described in the fluid domain to the elastic domain or solid domain of the material, then we can fully simulate a true printing process. Now moving to probably a more, I would say a less numerical model part of the story. Another trend beyond the simulation part to improve reliability of your printing process and material characters and material definition of the materials you're going to use. There is a strong move towards sustainability, and that is, you can almost say, I can almost say that this is something that would inevitably hit 3D concrete printing as a research topic, because we know the CO2 impacts and sustainability behind the production of cement and use of concrete. So companies are moving towards using pre-mixed materials and mortars to more sustainable compositions that would be using concrete. And in the very first test we had here at DTI, and I'm showing all the numbers I'm showing here, they are normalized data, because unfortunately I cannot share the mix design. It's still confidential within the project we are running. So the picture on the left with the green mix, we have a material that is running on, it's a mortar. This mortar uses white cement and some pigments. So I'm calling that number 1. So my cement content was 1. Once we started our test with concrete, we could reduce already by 6 to 7% the cement content of that mix, and also change the cement type. But then lately we went all the way to reducing by 31% the amount of cement content. Of course, you're replacing now all your fine materials, including cement and sand, with large aggregates. Of course, using large aggregates imposes different challenges in terms of equipment wearing and the extrusion, the quality of the extrusion process itself. But this is a trend that I would like to bring to the audience, because in order to make 3D concrete printing more competitive to the construction market, then there is a need to first make sustainable mixes that will at the same time not only be sustainable, but much cheaper than the mortars being used at the moment. I'm not saying that the mortars, and they will start, of course they will start competing. There are applications where pre-mixed mortars and custom mixed designs of mortars, they are necessary, because that gives you a nice small like feature resolution of what you're printing. When you're working with concrete, in our case with 8 millimeters aggregates, then your minimum resolution during a print becomes 8 millimeters. There are some there's a lot of differences. It's like getting a beautiful fine printer, and now you're making really chubby thick layers, and they look okay if you are from distance, but when you come closer, it's like you lose the sense of it's more architectural. Probably one of my colleagues, Thomas, who is an architect, would have a more technical comment on that. In my case, it is concrete. It's a material that's sustainable. I mean, using large aggregates, and we've been successful in running some prints with that. So just to showcase how the cement content has been decreasing over the mixes that we have developed and tested here at DTI. So these mixes A and B are within the mortar domain, where we had very high cement content. Mix B mix 1, the A uses a white cement. Mix B uses a calcined clay-based cement, and then you see later how does that impact on the CO2 figures of all these mixes. But when you go into concrete, that's mixes C and onwards, all of them have a reduced amount of cement content. Of course, we are adding large aggregates so that they're all extrudable, and the colors, again, I'll not go into details of these mixed designs, but the shades of gray you see there, they are mixed designs made with either different cement types or aggregate types. Now, when you look into the CO2 equivalent of these materials, likewise, as you're reducing cement content, you have a dramatic reduction of the CO2 footprint of these mixes. So we were in the order of almost 600 kilos per cubic meter. The second mix is quite specific. Again, we use the calcined clay cement, so it has we could increase the amount of limestone filler we had in the mix. But that detail aside, when you go towards concrete, and all of these mixes are using either ISM1 or calcined clay cement, you have a dramatic reduction of CO2 equivalent. And if you look specifically at mix F, it's the only one you can compare to mix B because they both have the same cement type, calcined clay cement type. Therefore, by default, you already get about 30% reduction on CO2 compared to ISM1. So this is just to spark the curiosity of those working with mortars and thinking about moving towards large aggregates, concrete printing. And I still call it 3D concrete printing, even though people say, well, this is a mortar, this is a concrete. I think that the fact that everyone has been using the same terminology is positive. So when you say 3D concrete printing, whether it's a mortar or concrete, for me, it makes no difference. You can call it micro concrete if it makes you feel more or less comfortable. So that's up to us. Okay, so this was all about the material part. When it comes to extrusion, there are two trends. The first one has been already developed by several companies, and we have done our own developments at DTI. The first one relates to continuous concrete processing. So how can you activate the material at the extrusion point in order to prevent anything that could go wrong throughout your streamline of material going to the nozzle? So how do you activate it so you can stack? And then how to benefit from simulation data from those simulation models I showed before in order to optimize your extrusion or the appearance of your extruded material. So I'm just highlighting two photos of an equipment we were running with, a normal progressive cavity pump for the mortar, a similar approach for a dosing pump, injecting an accelerating ingredient to the nozzle. And then in the nozzle, we have a mixing shaft with an injection inlet where both materials meet, and within 10-15 seconds of residence time in the shaft, they are mixed and ready to go. That means we can accelerate the mix and eventually stack the layers. So in the first video here, just showing one of the last columns we printed. The last print was actually a Christmas tree, and this will be released later. It was quite a fun print. We finished last Friday, but the idea was similar, to use a mixing nozzle, so to have a continuous concrete processing strategy. And regarding the use of simulation data to optimize extrusion, we use the CFD models, or CFD models can be used in order to give you information of what kind of strain rates or what kind of shear you have during the extrusion process. So in that case, you can custom design a nozzle geometry in order to reduce the amount of shear you have for a particular material. Of course, every material will have a best nozzle geometry. So instead of testing them all, we can run simulations, and this mix here that I'm showing this last in the video at the right-hand side, it's a mix that has up to 1,500 kilos per cubic meters of aggregates. I'm sorry, the video is a little jerky there, but it has up to 1,500 kilos of cubic meters of aggregates, with about 56% of that being aggregates up to 8 millimeters. And we accomplished to get an extrusion that is not rough, like to the point that you start tearing your material, because it takes less shear to crack a mix. I mean, during extrusion, when you're using larger aggregates. So you would have to increase your volume of paste or amount of mortar in that mix design in order to make it smoother to mix. But instead of doing that, which would be opposed to a sustainability approach, we modified the nozzle geometry in order to reduce the shear strains during extrusion, and then accomplish still a successful print. So if we move on into reinforcement, there is a presentation from TU Brunswick later during the PM event today, so I'll keep this one very short, and I borrowed a scheme that they presented in their last publication from Harold Clough and all the group from Brunswick. But bottom line, like reinforcement, to me, or to my understanding on 3D concrete printing, is the current topic, is the gold, I'm calling it the gold chase of 3D concrete printing. There has been a lot of work done towards understanding the material, and as I showed, there is work still being done on the numerical simulation part, but in order for concrete printing to reach a competitive business within the construction sector, reinforcement is necessary. The structures we have out there are mostly reinforced. There are cases, of course, of residential buildings you can reduce and you can go around reinforcement regulations just by printing. Yeah, you can print the shell of a column and then grout everything with a reinforcement afterwards. This has been done before, so my point here is not to say it's good or bad. What I want to show are trends towards how to fully integrate concrete printing and reinforcement strategies. So when you push button, you have an automated system that does something with your reinforcement. And the suggestions from Harold Clough and his group was that first there is a group of reinforcement strategy called concrete supports reinforcement. So you're printing with concrete and then placing the reinforcement in different directions, and still orthogonal reinforcement in orthogonal to perpendicular to the direction you're doing the printing is still the biggest challenge. There are different approaches, either by using screw systems, meshes, pins that are being shot into the material, or fiber reinforced concrete, for example. The second class is reinforcement supports concrete. So you create a stiff mesh and then you either print or use shotcrete technology around it. Alternatively, it goes a bit beyond 3D concrete printing, but there is mesh mold process from ETH Zurich, for example. And then last, there are systems that could be working simultaneously where you're doing a shotcrete or extrusion-based 3D concrete printing process, plus another method that is creating a reinforcement would be arch welding technology. And I think in that case, Chris, one of the organizers of the event, would also be the best person to give comments on the matter. So my suggestion is, if you're interested in the gold chase of 3D concrete printing at the moment, that is reinforcement, I suggest you have a look at least these 3 publications. I run a database called 3D concrete printing, a world of 3D concrete printing. I tried my best to keep it updated. So there is a bunch of, I think it's about 275 papers available on like what is available in terms of 3D concrete printing. So if you're interested in these papers or more, you can visit the database or just contact me either via LinkedIn or email, and I'll be more than glad to share information that I can share, of course. Here are some examples of one of the tests we've done at DTI, where we are printing around rebar. So in that case, it's reinforcement supports 3D concrete printing. We made a mesh. We created like a fill, different horizontal and vertical reinforcement layouts, and used the nozzle to print with concrete using large aggregates around these rebars going in different directions. And I'll jump to the point is, the idea here was to identify whether we would successfully reach a point where the reinforcement looks as good as cast concrete, where you have a perfect encapsulation of a reinforcement. And in some cases, yes. In some cases, no. If you see at the bottom where there is a hand holding a sample there, there is a bit of a gap on the side. This is something we are still working on. And not only us, I mean, as I say, there is a lot of research groups looking into reinforcement for 3D concrete printing applications. So, but that's an aspect that should be taken into account, whether you can really properly encapsulate. In that case, shotcrete 3D printing would be a good choice because you have a lot of pressure of a material against a rebar. Controlling the geometry is something else, of course. And then I'll just quickly go through the last 3 applications that came to me, of course, whether they are project partners in our development project in Denmark or not. First one was October 2020 by Perry Group using cobalt technology, where they're printing first 2-story building in Germany. Still using mortars here, but the idea would that be eventually all this mortar that's being printed can be upscaled to a concrete material. It doesn't take the advantages of the process in itself by having material save, increase of productivity, and so on. My point is just to show, hey, that's what's going on over the last 2 months in terms of real scale applications. There is so much I can do, or we can do here at DTI from the lab. The idea is to get all this knowledge from the lab and upscale outside, and it's good to see there are so many companies active on that matter. The second one is the project called Sphere by Sube in France. I mean, the company is Dutch-based, but the project is in Normandy, and they printed a total print time of 21 hours, not consecutive 21 hours. They were printing elements, and then made this sphere-based shape geometry using 3D concrete printing. And last, which is from the next presenter, and I won't talk much about this because Adam and the guys from 20 Additive Manufacturing would just lecture us on what are the challenges of actually deploying all this technology into the site. So this is just a teaser for the next presenter. So before I end, my takeaway message, and I hope the contents of this presentation, even though it's very short and there is so much I would love to talk about, I summarize all of what I said in these 4 lines. Regarding materials, there is a trend towards upscaling from mortars to concrete in order to improve sustainability. And if you're not upscaling from mortar to concrete, at least to reduce the CO2 emission or amount of binder you have on your current mortar. So you do not always have to go large aggregates, but that is one of the trends. Extrusion-wise, continuous concrete processing is still a topic of research. And I have to mention that companies like Baumit, X3, which do wonders in terms of active mixing into the extrusion point. Next, reinforcement, that the gold race is on, so it's up to us to go for the joint fight. And I wouldn't say there is a competition, of course, but there's still a lot of collaboration between different companies within the additive manufacturing in construction business. And the latest applications that I have shown, it just validates the fact, not validates, but verifies the fact that 3D concrete printing applications are still increasing at an exponential rate. And these will just get better or worse. I mean, it will just keep going up over the years to come, because the technology still needs a few developments to go on, and then topics like durability will come, standardization will come within the next, I would call, medium-term horizon. So here's how we are connecting the dots here at DTI. We have a development project called NextCon. That's the next generation of 3D concrete printing structures, and we are trying some of the results I showed here in this presentation. They are part of this project called NextCon, where we go and make experiments and evaluate everything from the material development all the way to the printing process and reinforcement strategies. But the link between that, and in order to make concrete printing reliable and robust, is a simulation tool. In that case, we can easily reduce the amount of effort that's necessary in order to start a print process or to get it rolling. And not only that, also to enable people to depart from pre-mixed materials and use their custom mix designs wherever they are in the world, because this in the end will be crucial for mainstream application of 3D concrete printing, that anyone with the locally available materials can develop a mix design that can be validated, verified first numerical simulation model, and then deployed to the construction market. Without a simulation model, this is also possible, but it would just require a bit more resource and testing, and the tests are quite large and heavy and expensive. So you either have the resource to do all these tests, or you rely on a bunch of numerical calculations to reduce the amount of effort you have to have when you're going on site. So we do the hard work in the lab in order to provide data to industry, just to hit the button and get a concrete printing running. So that's what I had for today. Thank you for your attention, and feel free to contact me, send questions. That was it.
Thank you for the lecture. I think the interesting thing with, say, the digital time, in a normal situation, when you're running out of time, I slowly would go to the person and they would feel the physical pressure. This doesn't work in digital time, so you can entirely neglect me. I'm waving, you're done, nothing happens. Thanks for the speech. And yes, you actually hit all the things I see happening as questions in this thing. I do have a lot of questions, but I'd like to have first the other concrete group to present, and then we may have some of these questions already answered. So Wilson, thank you for this, and stay in the system so that we can have a talk later if possible.
Of course.
I learned from Philip that there's one question from the audience which I'd like to use in here. So Philip, please raise the question.
Question addresses Wilson's presentation, and it reads, is it possible to live alter your concrete mix? For example, if you want a graded print, or need to adapt your properties depending on how the print is going, or so on. Is there any possibility of implementing it? And is there a possibility of simulating this?
The way, first in terms of implementation, the simple way we tried was actually by playing with amount of pigments. In that case, it doesn't affect the material properties, but in one of the columns I showed, it's not clear from the video, but if you see the column in our lab, we start like with a darker tone of gray and we go towards white over the height. This would be a way of exemplifying how you could make a functionally graded material in terms of colors, which is the simplest way because it doesn't affect much, again, properties on fresh state and would hinder your extrusion. But instead of injecting a pigment, we could be injecting an air entraining agent, assuming the material would still be stable over the printing process. So implementation-wise, yes, it's doable. Simulation-wise, as I mentioned, the two numerical models, especially the second one, in terms of evolution of elastic properties, it's a time and temperature dependent model. So if we can include the changes of material properties over time, in that case, including change of a mix design, which would include a parallel model into that constitutive model, then yes, it's probably easier to simulate than test.
Well, we not push you to a time estimation, huh?
Yeah, Wilson, thank you very much. I have a whole lot of questions that I want to ask you, but unfortunately we're out of time. We're going to have to move on to the next speakers. But can you please join me in thanking Adam, Tim, and Wilson for their kind of very insightful presentations.
Online.
Online, exactly.